Hello students, the continuation of electric circuit analysis lecture. Today's topic is resonant circuits. Myself S. Kotresh, Associate Professor, Department of Electrical and Electronics Engineering, Rao Bahadur Y. Mahabaleshwarappa Engineering College, Ballari. After completion of this lecture, the student will be able to explain the concept of resonance. Student able to derive expressions for bandwidth and Q factors. Able to draw the frequency versus reactance curves. A student is able to solve the problems and finding unknown parameters in the series and parallel resonant circuits. These are the contents of my topic: basic definitions, series resonance circuit, frequency versus reactance curves, Q factor, selectivity, bandwidth and its expression, examples on series resonance. Before going to the concept of resonance, we will discuss about few basic definitions. First definition, impedance. It is the property by virtue of which opposes the flow of AC current. It is measured in ohms. In AC circuits, impedance Z can be expressed as Z is equal to R plus J XL in RL series circuit. Resistance and reactance are perpendicular to each other in RL series circuit. In RC series circuit, Z is equal to R plus J XC, and in RLC series circuit, Z is equal to R plus J into XL minus XC, where XL and XC are the inductive and capacitive reactances respectively. XL can be written as omega L and XC can be written as 1 by omega C. Omega can be computed with 2 pi f. F is the frequency in hertz and omega is the frequency in radians per second. Impedance is the most important parameter in series resonance as well as in parallel resonance. Coming to the next definition, admittance. It is denoted by Y. It is a reciprocal of impedance. Y is equal to 1 by Z. Admittance will be useful in parallel resonance. Coming to the reactance. Reactance is the property by virtue of which opposes the flow of current in an inductive coil. It is denoted by X. It is also measured in ohms. In inductor, inductive reactance occurs. In capacitor, capacitive reactance occurs. Next definition, susceptance. It is denoted by B. Reciprocal of reactance is called as susceptance. B is equal to 1 over X. Susceptance also we are using in parallel resonance. Frequency, most familiar definition. The total number of cycles per second is known as frequency. It is measured in hertz. Time period, the total time taken to complete one cycle by an AC quantity is known as time period. It may be voltage or current. These are the few definitions which are essential to learn resonant circuit. Look at the diagram, phasor diagram. Impedance and admittance are represented like this with the triangles. First one is impedance triangle, you can observe resistance and reactance are perpendicular to each other. Its resultant will be Z. Z can be written as Z is equal to square root of R square plus X square. If it is a inductive reactance, it will be XL square. And its reciprocal is taken here. For conductance is a reciprocal of resistance, admittance is a reciprocal of impedance, and susceptance is a reciprocal of reactance. So this triangle is inverted here, and omega is the frequency. Let us talk about resonance. What is resonance and what do you mean by resonating frequency? Resonance is the condition at which the applied voltage and resultant current are in same phase. In another way we can define a circuit which exhibits unity power factor. See, when we are getting unity power factor, in AC circuits, whenever circuit behaves purely resistive, that means voltage, applied voltage and resultant current both are on the same phase, then the phase difference will become 0, that is pi value will be 0. Then cos pi power factor will become 1, because cos 0 is 1. This condition exists whenever the reactance will becomes 0. That means both inductive reactance and capacitive reactance cancels each other. Then the remaining circuit, in the circuit remaining factor is only resistance, the circuit with only resistance, then only we are getting the condition of resonance. Coming to the resonating frequency. A RLC circuit has a distinguishing property of resonating at a specific frequency is called resonant frequency. So it is also called as tuning frequency. Tuning means we are varying the L and C parameters to achieve resonating frequency. In electronic circuits vary the parameters L and C, then we can achieve the resonating frequency. Also, keeping L and C constant, vary the supply frequency, then we can achieve the resonant frequency. These resonating frequencies are useful in so many electronic circuits, especially for filtering purpose, and in radio receiving stations we are using resonating frequency. Coming to the circuit, series resonance circuit. You can observe R, resistance R, inductance L and capacitance C are connected end to end in series across AC supply. Same current flows through the resistance, inductance as well as capacitance. Current flows through the resistance, makes an voltage drop, that is called as VR. VR equal to I into R. Same current flows through the inductance. Inductance will have the inductive reactance. So the voltage drop VL is equal to I into XL. Similarly, same current flows through the capacitance. This capacitance will have the capacitive reactance. The voltage across capacitance is I into XC. The total current or maximum current can be calculated with supply voltage divided by resistance, Vs by R. This is a typical RLC series circuit. you can observe the second figure here, same figure, and I have considered LC circuit here, LC circuit, capacitor and inductor connected either way, either in series or parallel, we can achieve the resonating condition or resonance frequency. See here, the difference of voltages, voltage across inductor and voltage across capacitor is put together considered here. And whenever L and C will become short, when it will takes place, that I will explain in the next slide. Here, due to these two, when they are shorted, the reactance, total reactance will become 0. Why? The total reactance will become 0 because XL and XC cancels each other, because XL and XC are opposite in nature, equal and opposite in nature. Then only this status exists. XT is equal to 0, then the remaining circuit will have only resistance. This resistance will be connected across the AC supply, then it behaves pure resistive circuit. Concept of resonance. One can understand very easily how LC circuit works. What happens in between L and C? See here, this is an animated picture. One inductor and capacitor is connected. It is called as LC circuit. Most familiarly, it is called as tank circuit or tuning circuit. See here, what happens here? Current is flowing in both directions, two currents. One current is flowing towards inductor and one more current is flowing towards capacitor. What happens here? Both inductor and capacitor are the passive elements which can store the energy. They are called as energy storing elements. See here, an electrical energy oscillates between the magnetic field and the electric field. See here, electric field and magnetic field in between L and C. Electrical energy is oscillating. See, to produce the magnetic field in the inductor, current is required, which is provided by the discharging capacitor. See in this direction. I will repeat, the magnetic field generated in the inductor due to the current which is provided by the discharging capacitor. At the same time, the capacitor stores the energy in the form of electric field by the current produced by the inductor or magnetic field, collapsing magnetic field. At certain point, at some point, the inductive reactance will be equal to capacitive reactance. XL is equal to XC takes place. Then we are getting the resonant condition or resonance frequency. See here, at certain frequency, so-called resonant frequency, the inductive reactance of the circuit is equal to the capacitive reactance, which causes the electrical energy to oscillate between L and C. This will be going on as long as supply is on, and it is just give and take. So inductor gives the current to the capacitor and capacitor gives the current to the inductor. So whenever this status exists, XL is equal to XC, then we are achieving the resonant frequency. Then we'll go to the mathematical expression, condition for resonance. We know what is the condition. So inductive reactance is equal to capacitive reactance. So inductive reactance can be expressed as 2 pi FL, that is equal to 1 by 2 pi Fc. Cross multiply, F square is equal to 1 by 2 pi Fl into 2 pi C, 2 pi L into 2 pi C. So its product will become 1 by 4 pi square Lc. So finally evaluate F, that is the resonating frequency what we want, that is 1 by 2 pi root Lc. If you express, we can express in terms of omega r, that is radians, that is 1 by root Lc. So after understanding the concept of resonance, we will go to the few characteristics, frequency versus reactance curves. The frequency is taken on x-axis, reactance on y-axis. Here in the first graph, inductive reactance and frequency is taken. So what happens here? So the frequency is directly proportional to inductive reactance with respect to this expression, XL equal to 2 pi Fl. Whenever F is equal to 0, that is called as DC state. So at that state, the inductive reactance is also 0. If inductive reactance is 0 in the circuit, then circuit behaves like short circuit. As long as increase the frequency, if F increases, inductive reactance also increases, and it is directly proportional. If you plot a graph between them, it is linear and looks like a straight line. As long as frequency increases, inductive reactance also increases. It reaches to the infinity, and finally the circuit behaves like open circuit. See, resonance is the topic, it is included in the module number 1 as per VTU syllabus in ECA, electric circuit analysis. It is easiest topic as compared to other topics. Most of the questions in ECA, the problematic subject, it is a problematic subject, majority of the questions will be problematic one, and theoretical part, if you are expecting theoretical part in resonance, you can expect. So derivations, definitions, the chances of getting definitions and derivations, derivation of bandwidth and Q factor and simple problems you may expect from the resonance topic. Let us continue with this graph. As I told, as frequency is less, inductive reactance also less, and circuit behaves like short circuit. As I told, if frequency is increased, inductive reactance also increases, and it reaches to the, when frequency is infinite, inductive reactance also infinite. Then the circuit, inductive circuit behaves open circuit. Next, coming to the next graph, second graph. Here XC, capacitive reactance, is taken on y-axis, frequency on x-axis, and the expression for this XC is equal to 1 by 2 pi Fc. With respect to the expression, frequency is inversely proportional to capacitive reactance. So, frequency is inversely proportional to capacitive reactance. It is exactly opposite to the earlier. So, as frequency increases, the inductive reactance decreases. As frequency increases, capacitive reactance decreases. So, it looks like a hyperbolic curve. So, when frequency is less, capacitive reactance is more, and during that time circuit behaves open because Xc is greater, Xc is higher. It is vice versa, and later the circuit will become short. See this diagram. It is a graphical representation of both reactances. Both reactances Xc and Xl with respect to frequency are shown. So, Xl versus frequency gives this straight line, and Xc versus frequency will give this hyperbolic curve. Both reactances are meeting at this point. This point is called as resonating point. We are getting, or we are achieving the resonating frequency at this point, at which Xl is equal to Xc at this point. That means the intersection of two reactances Xl and Xc at this point, this is called as intersection point. At this point we are getting the resonating frequency Fr. So, at that point the inductive reactance is equal to capacitive reactance. So, here Xc is greater than Xl, that means circuit is highly capacitive in nature here, and here circuit is inductive, it is reverse, Xl is greater than Xc. Next graph, coming to the other characteristics, we can plot impedance versus frequency curve. As I told already, impedance Z is equal to R plus J into XL minus XC. It's an expression for impedance in RLC circuit. At resonance, the inductive reactance is equal to capacitive reactance. Both reactances were cancel each other. Then this imaginary part will become 0. Then obviously the impedance is equal to resistance. So, at the resonant condition we are achieving this. Then circuit behaves purely resistive in nature, and in series resonating circuit the impedance will be minimum and current will be maximum. So, this is the graph. The resistance is equal to impedance here. This is also called as dynamic impedance. The impedance which we are getting at point of at the point of resonance is called as dynamic impedance. Next graph is current versus frequency. So, as I told, if impedance is minimum, current will be maximum because it is inversely proportional. So, if impedance reduces, current increases. So, current will be maximum here. This point is the point of resonance, what we are getting here. There current is maximum. So, current increases, you see this, current increases when it is capacitive in nature, and circuit is capacitive in nature, because in capacitive circuit current leads. Later on, after achieving resonating condition, the current slowly decreases during this inductive nature. So, I is equal to V by ZL. Coming to the power factor. We know this definition. Cos pi is called as power factor in AC circuit. It can be defined as cosine of the angle made between voltage and current in an AC circuit is called power factor. So, voltage and current both are AC quantities. They are making the phase difference. That phase difference is determined by pi, the angle. If we are taking cosine of that angle, then we are getting power factor. Another definition is the ratio of resistance to the impedance is also called as power factor. See, in this waveform, one is voltage expression, another one is current expression. Voltage expression can be written as V m sin theta, theta is replaced by omega t, and I is equal to I m sin theta. So, voltage and current both are on the same axis. They are meeting here on 0 axis, and both are in phase with each other. Phase angle will be obviously 0 and power factor is unity. Coming to the quality factor. Quality. So, it is L by R, ratio L by R can be considered as quality factor in general. But by definition, we can define it is the ratio of maximum energy stored in an element to the maximum energy dissipated by an element of the circuit per cycle. We are computing for one full cycle, quality factor. So, maximum energy stored in an element divided by maximum energy dissipated in an element multiplied by 2 pi for one cycle. So, quality factor can be computed with these expressions. Q is equal to Q naught is equal to omega R by L. Omega R is the resonating frequency, L is the inductance, R is the resistance, and XL by R. If you have XL directly, we can calculate. And another expression is 1 by omega R into RC, and one more expression Q naught is equal to 1 by R square root of L by C. So, this can be how we got these expressions. So, we know that the energy stored, we are considering L as the energy storing element and R is the energy dissipating element, because always power is consumed in the resistor and power is stored in the form of energy in the inductor. So, I will take L and R initially and I will draw the circuit. It is an AC supply connected to the inductor and resistor, both are connected in series. Represent this one as L, R. This is the voltage and current I naught is flowing through this inductor and resistor. I will take the energy stored in the inductor, energy stored in inductor, I will call it as EL is equal to off into L into I naught square, off into L I naught square. I naught is the current flowing through the inductor, and energy dissipated can be written as ER, that equal to power dissipated into time. power dissipated into time. Power dissipated can be written as I naught square R divided by 2. It is RMS value. Straight away I have taken RMS value of power, it is half power I have taken here, into time can be written as 1 by F. So ER can be written as I naught square R by 2F. If you substitute these two expressions in the Q factor expression, Q naught is equal to 2 pi into energy stored in the inductor, I will write it as half L I naught square divided by I naught energy dissipated I naught square R by 2F. This two cancels, I naught square cancels. Finally, your expression will become Q naught is equal to 2 pi F into L divided by R. 2 pi F into L by R. So 2 pi F I will call it as omega R, resonating frequency, into L divided by R. This is one of the expression for Q factor. Q factor is used to check the quality of the circuit or series RLC circuit. In the similar way, we can take, instead of inductance, I will take capacitance. Just I will replace the inductor with capacitor C. And voltage across capacitor, I will take it as VC, voltage across capacitor. That means with resistance and capacitance also we can derive one more expression for quality factor. Here energy storing element is capacitor and energy dissipating element is resistor. As similar to inductor, I will take energy stored in capacitor. Energy stored in capacitor, I will write it as half C, capacitance C, into voltage across capacitance square, half C Vc square. Already we know the energy dissipated in the resistor. Straight away I will write ER is equal to I naught square R by 2F. Already in previous expression we have derived this. Substitute these two, energy stored in capacitor I will call it as EC, and the energy dissipated in the resistor is I naught square R by 2F. So you substitute in Q naught expression. So 2 pi into half C Vc square divided by half I naught square R by 2F. This is equal to, you know, voltage across capacitor can be expressed with I naught XC square, I naught square XC square. So 2 pi into half into C, keep as it is, Vc square can be written as I naught square XC square whole divided by I naught square R divided by 2F. So I naught square will go, and if you compute this expression you will get Q naught is equal to 1 by omega R into RC. So these are the two formulas we are using to find Q naught. An alternative expression for Q naught. An alternative expression for Q naught. We know that omega r is equal to 1 by root of LC. And we have the expression Q naught is equal to omega r L by R. This you call it as equation 1 and this you call it as equation 2. Substitute equation 1 in 2. We get Q naught is equal to, I will substitute in place of omega r, I will substitute this, I will split like this, root L into root C, this root LC into this, I will write it as root L into root L. L can be written as root L into root L divided by R. See, 1 root L and 1 root L will cancel, and this will be, I will put in 1 square root, root of L by C, and your expression, final expression will be 1 by R to root of L by C. It is also quality factor expressions. Totally, quality factor can be calculated with 3 formulas. One is Q naught equal to omega r L by R. Second expression, Q naught equal to 1 by omega r into RC. And third expression is Q naught equal to 1 by R square root of L by C. Students, you can use any formula, the result will be same. Either among the 3, any formula you can use to compute quality factor. Next, coming to the selectivity. So, selectivity is used to discriminate desired and undesired frequencies in the circuit. That is selectivity. And by definition, we can define it is the ratio of resonating frequency to the bandwidth of the resonant circuit. So, now what is bandwidth? So, most of the time in question paper, you may observe this question. Define bandwidth and derive an expression for the bandwidth. I will repeat. Define bandwidth of RLC series circuit, series resonance circuit, and derive an expression for bandwidth. So, first I will explain what is bandwidth. See, this is the curve, graphical representation of frequency versus current, and current will be maximum under resonant condition. This is the maximum point. So, I equal to V by R, that equal to V by magnitude of impedance, we can write, because as impedance is minimum, current will be maximum. Now, here there are 2 half power frequencies at this point and here, 2 points. Those 2 points are called as cutoff points of minus 3 dB. So, you can here observe here minus 3 dB cutoff, and these 2 frequencies, this one is called as lower cutoff frequency FL, this one is called as higher cutoff frequency FH. So, at those 2 points, the current will be 0.707 times of I maximum, that is Im by root 2, we can say. So, here definition of bandwidth. So, this width is bandwidth BW. The difference between 2 cutoff frequencies, upper cutoff frequency and lower cutoff frequency, FH minus FL, is called as bandwidth. So, here you can observe FL is lesser than resonant frequency, FH is greater than resonant frequency. If frequency is less than resonant frequency, the circuit is capacitive in nature. That means XL is smaller than XC. If XL is smaller than XC, omega L is smaller than 1 by omega C. Obviously, VL, voltage across inductance, is less than voltage across capacitance. I will repeat, XL is less than XC, omega L is less than 1 by omega C, and VL is less than VC. Up to here. Suppose the frequency is greater than resonant frequency. That is, frequency is greater than resonant frequency. Then the circuit behaves inductive. Here, reverse phenomena. So, here XL is greater than XC, omega L is greater than 1 by omega C, and VL is greater than VC. Whenever VL and VC cancels each other, then we are getting resonant frequency. So, both voltages are equal and opposite, and they will cancel each other. And power at these 2 points, so power equation will be P equal to I square R, and power at these 2 points is half of the total power. So, P is equal to I square R by 2 at these 2 points, that is at minus 3 dB points, at cutoff points. So, that you can see here with expressions. So, P power, total power divided by 2, and current at those 2 points is maximum current divided by root 2 times, that is 0.707 times of Im. Next, bandwidth can also compute with resonating frequency divided by quality factor. So, if you know the value of Q factor, if you know the value of resonant frequency, the ratio of that will becomes bandwidth. So, I told already inductive and capacitive, when it will be inductive and when it will be capacitive. So, Z is equal to root 2 times of R, it is reactance will be plus R, it is inductive in nature, and here it is capacitive minus R, it is capacitive in nature. Then how to find 2 individual frequencies? So, higher cutoff frequency and lower cutoff frequency. If you are having the values of R and L, we can use this expression to compute the frequency, higher cutoff frequency, plus R by 2L plus square root of R by 2L whole square plus 1 by LC. Same formula with negative sign, lower cutoff. Because it is lesser than resonant frequency, we have to use minus. It is greater than resonant frequency, because higher cutoff will be greater than resonant frequency, we have to use plus. So, formula is same, only the signs you have to use, plus for greater frequency and minus for lower frequency. Next. So, let us derive an expression for bandwidth. So, an expression for bandwidth. So, we know that current, maximum current, I will call it as I naught, is equal to V by magnitude of Z, applied voltage divided by impedance. It is also equal to V by R because Z is equal to R under resonance condition. Also, we know that current at minus 3 dB point, that is at half power point, I naught equal to I naught by root 2. I naught equal to I naught by root 2. So, in place of I naught, I will substitute this V by R over root 2. This is equal to V by root 2 times of R. Root 2 times of R. Now, this you call it as equation number 1. This you call it as equation number 2. Compare equation 1 and 2 here. V by magnitude of Z is equal to V by root 2 times of R. V and V cancels and we can write root 2 R is equal to magnitude of Z, that can be written as root of R square plus XL minus XC whole square, that I will write it as omega L minus 1 by omega C whole square. Now, squaring on both sides, you will get 2R square is equal to, if you squaring on both sides this one, this root will cancel, the expression will be R square plus omega L minus 1 by omega C whole square only. Send this R square to this side. So, 2R square minus R square, only R square. This is equal to omega L minus 1 by omega C whole square. Now, this plus or minus R I will take. This will become omega L minus 1 by omega C, square root of this. Here, one frequency, using frequencies, two frequencies, one is higher cutoff frequency, another one is lower cutoff frequency. I will form two expressions for this, one for plus R, another one for minus R. So, I will write plus R expression as omega 2L minus 1 by omega 2C. Call this one as equation number 3. Next, similarly minus R expression omega 1L minus 1 by omega 1C. This you call it as equation number 4. So, with this plus or minus R, I have formed two expressions. One is for higher cutoff frequency and another one is for lower cutoff frequency. Plus R, it is inductive. At this point, it is inductive circuit. This will be, and at this point, it is capacitive in nature. Now, in order to get the bandwidth expression, once we have to add these two expressions. Later, we have to take a difference of these two expressions. First, add equation 3 and 4. I will get, if you add R with minus R, you will get 0 is equal to omega 3 plus 4. So, omega 2L plus omega 1L. So, omega 2L plus omega 1L. Next, plus 1 by C I will take outside, minus 1 by C I will take outside from this, and within the bracket you will get 1 by omega 1 plus 1 by omega 2. This is equal to 0 already is here. Okay. Next, I will take L from this. L is outside. I will take L common. It will be omega 2 plus omega 1 minus 1 by C. It is omega 1 omega 2 LCM. In the numerator, omega 2 plus omega 1. Divide above expression with L, you will get divide by L above equation, you will get omega 2 plus omega 1. I will send to this side, it will be 1 by LC into omega 1 plus omega 2 by omega 1 omega 2. This and this cancels, omega 1 plus omega 2 and omega 1 plus omega 2 cancels each other, and this is equal to finally 1 by omega L, 1 by LC I can write it as omega naught square. This is equal to omega 1 omega 2, and omega naught is equal to root of omega 1 omega 2. This is one of the expression, and sometimes we can write it as omega r also in resonating frequency. So with this expression we came to conclusion, resonating frequency is the geometric mean of two half power frequencies. I will repeat, the resonating frequency is equal to the geometric mean of two half power frequencies. This is one expression we got. Let's continue this. So if you are computing subtraction of these two expressions, 3 minus 4, you will get the expression, compute this, and finally the bandwidth expression omega 2 minus omega 1 is equal to r by L you will get, and f2 minus f1 is equal to r by 2 pi L. This is the expression for bandwidth. So the following points are summary. So whenever we are discussing series resonance, these points to be remembered. Inductive reactance is equal to capacitive reactance in series resonance, and impedance is equal to resistance, and current is equal to I naught equal to V by R, and voltage across inductor and capacitor cancels each other, and finally VR equal to applied voltage. So problems we will discuss in the next lecture.